Hello, everybody. This is Fausto Vaninetti speaking and working for Cisco Systems. A few years back, I was a director in the board of SDC Europe. In today's session, I will talk to you about 64 gig fiber channel and how it is different from previous implementations of the fiber channel technology. So let's get started. Fiber channel, as you know, is a high-speed data transfer protocol providing in-order and lossless delivery of raw data blocks. It is obviously primarily used to connect data to servers through storage area networks within typical enterprise public sector data centers. Fiber channel networks are also known as switched fabrics, and the reason for that is simple. Switches in the same network operate in unison as one big switch with shared knowledge and awareness. Fiber channel is based on a 5 layers model, and this has facilitated and still facilitates protocol evolution. It's clearly a storage optimized protocol with a large install base. I believe we can estimate that currently there are about 30 million fiber channel ports in service in the world. And this technology is still under active development. The main standard body for fiber channel is INSET under the group T11. Then we have the Fiber Channel Industry Association, which is possibly the marketing organization for fiber channel industry. And finally, SDC. SDC does a little bit of standards, but it's also the educational organization for everything related to storage and IT in general. So fiber channel evolved over the years from its inception at the end of last century. It evolved in 4 different ways. The first one, the speed. We moved from an initial 1 gig fiber channel, and currently we are shipping products that run at 64 gig fiber channel. But fiber channel also went through the compute form factor transition. Initially, it was just bare metal servers, then virtualization arrived, and more recently, containers. Fiber channel can play a role independently from the compute form factor that you are using. I also want to talk about the protocol transitions, because at the very beginning, fiber channel was transporting SCSI protocol. But then other protocols started to be transported across the same network. And the latest one is NVMe. So NVMe is today another upper layer protocol that can run over a fiber channel network. And the first direction of evolution for fiber channel is services. What can a fiber channel network deliver beyond simple connectivity? And in here, I would talk about things like deep visibility for your traffic and analytics, congestion prevention, intrinsic security with anti-counterfeit technology and secure boot, or maybe encryption for data in flight, traffic engineering, segmentation, and self-driving storage area networks with detect, react capabilities. So the first question I would try to answer is, do we really need 64 gig fiber channel? And the answer is yes. I'm not saying that everybody needs 64 gig fiber channel today, but most likely everybody has a desire to move to 64 gig fiber channel for the upcoming future. Clearly, 64 gig fiber channel delivers its best when you think about bandwidth angry and latency sensitive primary workloads like mission critical databases or highly virtualized servers, or maybe artificial intelligence and machine learning applications. When you have state-of-the-art servers with PCI Express Gen 4 slots, a dual-port HBA at 64 gig will be able to give you the best possible utilization of the available bandwidth, and up to 80%. By offering higher bandwidth, higher throughput, and lower latency, 64 gig fiber channel is also the ideal friend for NVMe fiber channel. So if you are moving to this new protocol, it comes pretty natural for you to consider 64 gig fiber channel as your preference. In terms of cabling infrastructure, 64 gig fiber channel can lead to some optimization. For example, instead of having 10 ISLs running at 32 gig, you could have only 5 running at 64 gig. And 64 gig fiber channel preserves the distances that we are used to with 32 gig fiber channel. 64 gig fiber channel also comes with a better efficiency in terms of energy consumption. So even if it is minor compared to previous generations, it is still something. So 64 gig fiber channel can be considered a more sustainable technology than its predecessors. But in my mind, the main reasons organizations are really considering 64 gig fiber channel is because they want to future-proof their network. Maybe they will not use their networks at 64 gig fiber channel today, but clearly they might have a need in the next couple of years. So they want to be ready without replacing the network when the need emerges. And that's the main reasons we see organizations to deploy 64 gig fiber channel networking today, in many cases using 32 gig fiber channel SFPs. Fiber channel, as I said, is built around a 5 layers structure. The lowest layer, called the Fiber Channel 0 layer, is the physical layer. It's where the media, the transmitters, and the receivers all live. The standard that describes in detail how you should implement the Fiber Channel 0 layer is called Fiber Channel Physical Infrastructure, and then a number. The number is aligned with the Fiber Channel generation. So for example, for 16 gig fiber channel, we had the Fiber Channel Physical Interface 5 standard. For 32 gig, we had the Physical Interface 6 standard. And for 64 gig fiber channel, we have the Physical Interface 7 standard. Of course, there is also a parallel implementation, 4 times 64 gig, and that comes with a separate standard with a final P. This is also known as Gen 7. So 64 gig fiber channel is often referred to as Gen 7. Sixty-four gig fiber channel can be described with some key capabilities. First of all, it doubles performance compared to previous bit rates. So we can go up to 6400 megabytes per second on a single port. 64 gig fiber channel devices can be smoothly inserted into an existing install base because there is backward compatibility with older generation of the protocol, namely 32 gig, 16 gig, and even 8 gig fiber channel. It's a plug and play approach with the existing infrastructure. 64 gig fiber channel also delivers investment protection because you can reuse the cabling of your data center. Transceivers are still SFP+, connectors are still LC connectors, and distances are the same as 32 gig. In terms of signal quality, 64 gig fiber channel delivers something really great. The bit error rate is below 10 to the minus 15. And this is described in details into another standard, which is not the physical layer standard, and it's called Fibre Channel Fabric Services 5. On this table, I try to summarize the changes that happened when we moved from the original 1 gig Fibre Channel implementation up to the 64 gig Fibre Channel implementation. And now the goal for Fibre Channel has always been the same. For every 1 gig of signaling rate, we want to deliver 100 megabytes of throughput. And every time we double the speed, we want to double the throughput. So moving from 1 gig to 2 gig, 4 gig, and 8 gig was essentially just an increase in the bit rate. All the rest, the line coding schema, the modulation format, was kept exactly the same. But when 16 gig Fibre Channel was introduced, a couple of changes happened. First of all, the line coding moved from 8B 10B to 64B 66B for higher efficiency. And also, forward error correction was introduced as an optional element, but if you wanted to enable forward error correction, you had to follow the standard, and that was the Fire Code FEC standard. When talking about 32 gig Fibre Channel, another couple of changes happened. Again, the line coding evolved to a different model, 256, 257, and the forward error correction implementation was made stronger by using a Reed-Solomon algorithm. But the biggest change has now come with 64 gig Fibre Channel. In fact, for the first time in history, we changed the modulation format. It's no more NRZ, no return to zero, but it's now called PAM4, Pulse Amplitude Modulation for levels. And also, we are using gray coding. Now, another change associated with that was an evolution to a better Reed-Solomon schema. It's still a Reed-Solomon algorithm for error correction, but it's a little bit more powerful than the predecessor. So those two changes are strongly interrelated. And in the next few slides, I will go into the details of all of that. So modulation change. As I said, up to 32 gig Fibre Channel, the modulation was always the same, no return to zero. But at this point, when considering a move to 64 gig Fibre channels, the standard bodies had two options on the table. One, keep doubling the bit rate, preserve the same modulation, but double the bit rate on the wire, on the optical cable. The second option was to change the modulation format and to move to something more efficient like PAM4. This would allow to preserve the bit rate, to preserve the signaling rate on the wire, but doubling the bit rate, which is essentially what we want. In making the decisions, cost and challenges have been taken into account. And the final go was to select PAM4 modulation with a similar signaling rate at 32 gig Fibre Channel. To say it in simpler terms, with NRZ, you transmit zeros and ones. They are the only two shapes within any transmitted symbol. And so the baud rate is equal to the bit rate. But with PAM4, every symbol can take up 4 different shapes, 4 different levels. And to represent 4 levels, you need 2 bits. This means that for every symbol, you are actually transmitting 2 bits of information. That's why the effective bit rate is double the symbol rate, is double the baud rate. I think a visual will make it much more clear for you. Here you see 8 gig, 16 gig, and 32 gig fiber channel using NRZ modulation schema. And in this case, the bit rate and the baud rate are identical. But when we move to 64 gig fiber channel, the baud rate is half the bit rate. So the baud rate is more or less the same as 32 gig fiber channel. But now every symbol equals 2 bits. So the bit rate is double than before. Pulse amplitude modulation with 4 levels is not something really new. In the past, we have seen the adoption of this kind of modulation schema on various transmission technologies. For example, Ethernet 100 gig base T was using PEM at 3 levels. 50 gigabit Ethernet uses PEM4, just like 64 gig fiber channel. And we even have implementations using 16 levels of for PEM. And this is the case for 10 gig base T. Now, the reason to adopt PEM4 for 64 gig fiber channel is quite simple. Essentially, we are trying to preserve bandwidth efficiency. We don't want to increase the symbol rate. But as a trade-off, we are accepting a reduction in the noise tolerance. And that means that we need to introduce some new tools in order to counteract the signal-to-noise degradation. We need to find a solution to improve the bit error rate to a level that is considered acceptable for this transmission protocol. So we can explain this signal-to-noise degradation by looking at the eye diagram, which is essentially an envelope of all the optical pulses that get received by a receiver. With non-return to zero, you have only 2 levels. With PEM4, you have 4 levels. So as you can see, the eye diagram is essentially now divided. You actually have multiple eye diagrams. And if you consider that you have noise into your link, you can understand that the chances to make a mistake in your decision about the level go up significantly. So how to compensate for that loss of signal-to-noise ratio? Well, the solution is forward error correction. But before talking about that, there is something new coming with 64 gig fiber channel. When you have one symbol with 4 levels and every symbol gets represented by 2 bits, the natural representation would be 0, 0 at the bottom, 0, 1 for 1 level, 1, 0 for 2 level, and 1, 1 for the 3rd level. Please note that when you move from one level to the 2nd level, you have 2 bits that need to change. This means that if you make a mistake in selecting that specific level, you are not going to get 1 bit error. You're going to get 2 bit errors at the same time, which is not really nice. And so by applying in gray coding, you can actually solve that issue. In gray coding, you swap the equivalent bit representation for your levels. So for level 2, you have 1, 1. And for level 3, you have 1, 0. In this way, even if you make a mistake in your decision for the level, for the transmitter level, you actually make a single bit error. So gray coding is a way to make sure that even if you get an error, it's a single bit error, not a double bit error. Now, the solution to reduce as much as possible the number of possible errors comes from forward error correction. And forward error correction is a set of very complex mathematical algorithms that perform corrections, allowing for recovery of one or even many bit errors in the same transmitted stream. The typical use case is to make transmission links much more robust to noise and other potential challenges. Forward error correction was introduced as an optional element for 16 gig fiber channel. It has become mandatory at 32 gig and now 64 gig fiber channel. The way it works is essentially to add redundancy to your data. Rather than only focusing on transmitting the data of interest, you add more data that through some mathematical computation can be used to extrapolate the data that were originally transmitted. Reed-Solomon has created a very nice model for forward error correction. It delivers great correction capabilities without introducing a lot of latency. And so if we focus on 64 gig fiber channel, for example, the Reed-Solomon schema that was adopted can allow to correct up to 150 error-read bits out of 5,140 bits transmitted. This means that you can receive a signal with 10 to the minus 4 bit error rate before applying the forward error correction decoder. When you apply decoding, the bit error rate will go down to below 10 to the minus 15. So 64 gig fiber channel has forward error correction, but even 32 gig fiber channel had forward error correction. And both of them are Reed-Solomon type. So what's the difference between 64 gig FAC and 32 gig FAC? Essentially, three differences. The first one, at 64 gig, we leverage gray coding. It was not there at 32 gig. It was not considered required, and it was not needed because every symbol was 1 bit. In order to accommodate a stronger FAC, we needed more bits for parity. And that's why the symbol rate of 64 gig fiber channel is not really identical to 32 gig fiber channel. It is a little bit higher, 3% higher. The final symbol rate is 28.9 gigabaud. And third, by using the new Reed-Solomon FEC implementation with a code word of 544 symbols and original data 514 symbols, we can correct up to 15 symbols, 10 bits each. And this makes up for the 150 bits that can be corrected at best. Now, the coding gain from this implementation of forward error correction is significant. We can achieve 5.4 dB of improvement in the signal to noise ratio. So as you understand, by moving to PEM4, we have a decrease in the optical signal to noise ratio. But by using forward error correction, we are going to recover that difference. And all of that happens by introducing minimal additional latency, that is a little bit more than 100 nanoseconds for forward error correction processing. And all the mathematical computation can happen within circuitry that is not really adding to the power consumption of your devices. Another way to explain how things work is well represented on this slide, where you can see what happens with the traditional non-return to zero transmission at 32 gig and compare it with what happens with PAM4 transmission. So the signal comes in on your pin photodetector, goes through a transimpedance amplifier, and it can be represented with its eye diagram. At 32 gig, the eye diagram is pretty simple because you have only 2 levels. At 64 gig, the eye diagram gets more complex, and you have actually 3 eyes into the same slot. Then we go to the decision threshold. We need to decide if the received symbol is a 0 or a 1. We need to decide if the received symbol is a 0, a 1, a 2, or a 3. Now, for 32 gig, after the decision threshold, we go directly to the FET decoder. For 64 gig, before going there, we need to go through the gray decoder. So there's an additional step. As you can understand, 64 gig fiber channel with the new modulation schema presents more challenges than previous generation of fiber channel technology. And I want to present you the differences between the past and the present day technology. So, for example, every fiber channel speed supports speed negotiation. This is required in order to achieve plug and play and backward compatibility. So link speed negotiation is present at 16 gig, 32 gig, and 64 gig. However, at 64 gig, we have also a phase called link training, and this is mandatory. Link training was not required at 16 gig and 32 gig fiber channel. Link training is essentially an adjustment, a fine-tuning to the receiver parameters so that you can improve the bit error rate. And how do you do link speed negotiation and link training? You do that using transmitter training signals. They are specific frames that contain information that the 2 end nodes on the same link will exchange to negotiate the speed and negotiate the other parameters like the threshold on the receiver. Now, TTS was optional at 16 gig. It was required at 32 gig for link speed negotiation, and it is required at 64 gig for both link speed negotiation and link training. Forward error correction was optional at 16 gig and is now mandatory for both 32 gig and 64 gig. From the implementation point of view, other changes happened. For example, in the past, we used to have analog clock data recovery and analog filters with a single decision threshold. Jitter was pretty well tolerated, and the signaling was NRZ. 32 gig fiber channel is the same from this point of view, but with 64 gig fiber channel, changes happened. We need to move to digital clock data recovery and digital filters, digital signal processors. Now we need 3 decision thresholds rather than a single one. Jitter has become much more critical, and we are using PAM4 signaling. From the optical point of view, new parameters have been introduced for 64 gig fiber channel. So in order to assess the quality of the shape of your pulses on the receiver, new parameters have been introduced. And for the future, in terms of implementation, we expect to see, let's say, a combination of elements to be happening inside a single chipset. So the clock data recovery unit, the driver, and the transimpedance amplifiers most likely will end up into the same chipset moving forward. The power bring up sequence at 64 gig fiber channel is a lot different than what it used to be at 32 gig fiber channel and previous speeds. I will not really go into the details because it's quite complicated, and the standard specification is very long in describing the whole new process. However, the one thing I want to make clear is that for the first time at 64 gig fiber channel, you need to tune optical parameters, specifically receiver thresholds. This was not required before, but of course, it takes time. You need to try, see result, try again, and maybe change again, and then see the outcome. So the key difference I want to point out between 64 gig fiber channel and previous speeds in terms of port bring up is that now it takes a few seconds before a link can be operational. We say mission mode when we start transmitting fiber channel frames. And this is because the speed negotiation is a pretty fast process, and it takes less than 1 second. And this is the same for 16 gig, 32 gig, or 64 gig fiber channel. But at 64 gig fiber channel, a few other things need to happen. First of all, you need to change from NRZ to PAM4 modulation. Second, you need to adjust the decision thresholds on receivers. And according to the standards, you need to respect a maximum timer, which is up to 10 seconds. Now, practical devices are faster than that, so most likely you can consider 5 seconds as the norm, but the standard would allow up to 10 seconds just for this phase. So keep this in mind because this is a key difference compared to the past. 64 gig fiber channel transceiver are tri-rate, 64 gig, 32 gig, and 16 gig. They clearly accept both NRZ and PAM4 modulation because PAM4 is only used at 64 gig. For the other 2 bit rates, you need NRZ. The transceiver itself is expecting to receive an electrical signal that already includes gray coding, FEC encoding, and the proper modulation. So there is no transit of modulation schema happening on the transceiver itself. If the modulation needs to change from NRZ to PAM4, that will happen on the motherboard of the switch itself, not on the transceiver. And in order to compensate for the reduced tolerance to jitter, 64 gig transceivers implement a clock data recovery unit in both directions, whereas in the past, we only had a clock data recovery unit in one direction. Clearly, there are multiple standards that need to be respected for 64 gig transceivers, and they are mentioned here on the right of my diagram. In terms of adoption, 64 gig fiber channel is clearly starting from inter-switch links. That's where you can deploy 64 gig fiber channel today. But by the end of this calendar year, we expect to see disk arrays with 64 gig fiber channel target ports. And so for the next year, we will possibly see someone adopting servers with 64 gig fiber channel HBAs. This adoption model is the same as in the past. When a new bit rate, when a new technology arrives for fiber channel, it starts from the network, moves to the target, and then to the hosts. This is the logical progression in terms of adoption. I already said that 64 gig fiber channel is backward compatible as a technology. And so if we talk about a single switch port that is capable of 64 gig fiber channel, that switch port will support 4 bit rates down to 8 gig fiber channel. Of course, the transceivers themselves only support 3 speeds. So a 64 gig fiber channel SFP will only support 64 gig, 32 gig, and 16 gig fiber channel. But you can also use a 32 gig SFP inside a 64 gig switch port. And in that case, you will be able to go down to 8 gig fiber channel. Some vendors can also support 16 gig fiber channel SFPs, but in that case, the only two available speeds will be 16 gig and 8 gig. 16 gig 64 gig fiber channel switches can be connected to same bitrate switches or older switches operating at a different speed. At the same time, they can be connected to HBAs that can be very new, operating 64 gig fiber channel, or they can be a little bit older and operate at 32 gig, 16 gig, or even 8 gig fiber channel. And for modular network devices called directors, there is also a possibility to combine 64 gig line cards with previous generation line cards. Clearly, the backward compatibility is vendor dependent, so you need to check with your specific vendor, but it is possible that you can have old generation line cards and new generation best of breed line cards coexist within the same chassis. When talking about fiber channel, we cannot avoid discussing buffer-to-buffer credits. They represent the flow control mechanism for the fiber channel protocol. Essentially, before transmitting a frame, you want to make sure that that frame can be received on the other end. That is the goal of buffer-to-buffer credits. Now, the longer you want to transmit your frames, the more you need buffer-to-buffer credits if you want to keep the link full and have an efficient transmission. There are formulas that can give you exactly the number of buffer-to-buffer credits needed for every specific situation. But typically, engineers use a rule of thumb. And the rule of thumb is pretty simple because if you remember one value, all the others will come through pretty easily. The value to remember is that when running a 2 gig fiber channel, you need 1 buffer-to-buffer credit for 1 kilometer of distance. If you double the distance, you need to double the number of buffer credits. If you halve the frame size, you need to double the number of buffer credits. So, for example, when running at 64 gig fiber channel with an average frame size that will be 1 kilobytes approximately, you would need 64 buffer-to-buffer credits per kilometer. So in the scenario where you have 2,000 buffer-to-buffer credits on a port and you want to run 64 gig fiber channel with an average frame size, your maximum distance for full link utilization will be about 32 kilometers. If you go longer than that, you either have more buffer credits or your links will not be fully utilized. So the point is, when moving from 32 gig to 64 gig fiber channel, remember, you need to double the number of buffer credits if you want to keep the same distances. Another change, another improvement coming with 64 gig fiber channel is serialization delay. Clearly, this is the time it takes to put bits on the wire. Imagine you want to transmit a full-size frame, 2148 bytes frame. And if you do that at 64 gig fiber channel, that will take you 612 nanoseconds. But if you do that with 64 gig fiber channel, that will take only 297 nanoseconds, half of the 32 gig time. This is the implication of moving to a higher bit rate in terms of serialization delay, which in the end is a contributor to the overall link latency. Another benefit coming from fiber channel at 64 gig is an improved power efficiency, because considering different devices from different vendors, essentially you can see that 64 gig fiber channel takes approximately the same power as 32 gig fiber channel devices. However, you double the bandwidth. So the power efficiency is actually improving by a factor of 2. In terms of my final considerations, I want you to remember that 64 gig fiber channel is a lot different from its predecessors, but at the same time, it is fully backward compatible. The key difference is the change in the modulation schema from NRZ to PEM4. And this comes with far-reaching consequences on product level design. Forward error correction has now become a critical element of any fiber channel solution because it's the only way we can guarantee an adequate bit error rate on the transmission link. And future speeds in the fiber channel world will clearly mutuate and learn from the lessons we have all received from implementing 64 gig fiber channels in real products. 64 gig fiber channel also introduces more benefits to storage networks, like better power efficiency, reduced serialization delay, so reduced latency, and even more than that. Hopefully, my presentation was interesting for you. And if you want to reach out, my contacts are mentioned here on this slide. So please remember to take a moment and rate the session so that the organization can see how to improve for the next delivery. Thank you very much for your time.